This is a presentation on behavioral AI for indie games. And a quick introduction, this will just be a very high-level interview of several behavioral AI techniques, and it's intended for designers as much as programmers. We're not going to get into nitty-gritty technical details, but I want designers to be aware of the different options that are available for behavioral AI because the right AI technique makes a game easier to finish, reduces the load in the long run on the programmers and designers, and good AI makes a game more interesting to players. So the topics we're going to go through in this talk are just some prerequisites or background info on behavioral AI in general, and then a number of behavioral AI techniques or approaches. That includes the decision tree, rule-based systems, state machines, behavior trees, game trees, hierarchical task network planners, goal-oriented action planners or GOAP, utility AI, machine learning, and AI directors, just as a little bonus. So this is what I was talking about, Julian. What is behavioral AI? It is a system to make an agent, such as an NPC, decide on actions and execute those actions to give the appearance of being intelligent and being autonomous. So this is different from generative AI, which attempts to essentially second guess what the requester is asking for next. In other words, like answering questions via ChatGPT or generating an image based on a prompt. So this is not that. This is the kind of AI that is used to control enemy opponents in games or companions or anything that has entities in the games that need to appear like they're thinking and doing things. But good behavioral AI needs to be challenging but beatable, comprehensible to the player, and I'll go over that in a bit, and it needs to be interesting. So to do this, I recommend choose the simplest AI technique that actually gets the game, that gets your idea across for what you want the AI to do. So when it's simpler, it's faster and easier for your programmer, easier to debug, easier to go back and maintain over time. But while you do this, you can maximize perceived complexity. That is, players will often assume agents are smarter than they are. One good example of this is barks. For example, you can have enemies in a scene. They might not have implemented being able to hear the player, but if they happen to be near the player with a simple distance check, they could bark something like, "I heard something." And the player is going to assume that the agents actually heard the player. So take advantage of things like this when you're designing your behavioral AI to really make it simple to implement, but look like they're doing a lot more than they are. Another example is when an agent decides to take some action, such as running for cover or attacking the player. If you just delay a random amount, maybe somewhere between half a second, it simulates reaction time and it just makes them feel a little less robotic, like they're thinking a bit and reacting before they act. But when you do this, you want to make sure that what they're doing is kind of apparent to the player, because if the player sees them do something, even if it's really clever, but it doesn't seem to make sense, at least how the player can discern sense, the player will think that the AI is bugged. So you want to find a balance between these two things. The way you go about deciding what to do is having your agent know what the current game state is. And that is called the world model. And it involves internal information like how much health do I have? How much ammo do I have? What do I want to accomplish? and external information, such as how is this level laid out, or what are the pieces on the game board if you're doing a board game style game like chess or checkers. And a lot of that external stuff can come from a sensory system, which is a way of gathering information about the external world. And we're not going to go over that at all. I'm just mentioning that because that is an important aspect of behavioral AI. And many AI techniques rely on memory, which is just a record of past world states and past decisions. So some use it, some don't. And some AI also use something called a blackboard. That's where different parts of AI can share information that helps them make decisions. So these are just terms that are good to be aware of, and your programmer might talk about, or if you are a programmer, uh, these are good terms to look up when you're researching AI. So the most basic form of AI in many games with like units that move around is just simply movement. It may even be sufficient to just move an agent to a position and play an animation. Far Cry is a good example of that. When the NPCs don't have anything to do, like they're not running around attacking the player, they will look for something in the scene that is tagged with an animation. For instance, there might be a pickup truck, and they just move to the pickup truck and play whatever animation is specified on that, which might be to open up the hood and tinker around on the engine. And it makes it look like the agent is smart and decided, oh, I need to tune this engine. But really, they're just moving and playing an animation. Very often in a lot of games, that's all you need to do for AI to make it look smart. But you can combine it with simple decision making, like where do I go? Um, when you are developing the world model for movement, the four things you need are, the map, where you can move, what the obstacles are, where you currently are, and where you're headed. The ways of moving are waypoints, where you could just move a unit in a straight line or across it from point to point. And that's very simple because then you're just doing an interpolation over time from point A to point B. Or you can do something called steering behaviors, which are very simple. Uh, it's a very simple technique of just pointing toward or away from a goal position and just moving toward it. Did we have any questions? Uh, Flocking and formations are very often done with steering behaviors. But on top of steering behaviors, we very often use something called pathfinding. And there's a reason why I'm going to go over pathfinding really quick before the rest of behavioral AI. So pathfinding is important because movement is fundamental to so many games, RTSs, shooters, and pretty much any game with units that can move around. But the same techniques that you use for determining how to move are fundamental to other types of AI too. Because pathfinding is a graph search. And for designers, that you don't really need to be aware of that, but this is helpful for programmers to realize. Um, there is something called a heuristic function that graph searches use to determine, which path down this graph of nodes should I follow for the most likely best outcome. For example, a heuristic function for pathfinding might be, does this get me closer to the goal? Or if it's a heuristic function for a different type of graph, like companions, does this choice improve my relationship with the player? So pathfinding looks like this. This is just a grid-based example of pathfinding when you're going from green to red, and it just chooses squares to go to that get you there most efficiently. But that's really just a graph. So when a pathfinding algorithm searches the graph, it searches all of these directions, these arrows, and finds the path that's the most efficient to get to the goal position. And that is why pathfinding really has been such a focus of AI for decades. So we'll move to the first technique here. And this one doesn't actually use pathfinding. It's called a decision tree. And Pac-Man is an example that uses a decision tree. Dialogue is also another example of using decision trees. So these trees look kind of like this. So this is an example of a decision tree for a combat unit where you would start at the top and you have a simple yes no question. Typically, these decision trees are binary. They're all yes no questions. If the if the unit can't see the player, it just wanders around aimless. If it can see the player, it goes to the next decision. Then it asks, am I close to the player? If not, it'll close in. But if they are close to the player, it'll do some attack move, maybe play an attack animation. And you can see how in pseudocode here, it's very simple to implement these. In fact, if we look at the pros and cons, decision trees are fast to run, really easy to implement, and simple to understand. If we go back here, that's pretty simple to understand how it works and how it's making the decisions. But the disadvantages are it can obviously be repetitive and predictable. It's inflexible. You have this one set of yes no questions and it always follows those. And it can be difficult to scale if you have a lot of yes no questions. I should notice that predictable is not necessarily bad. When something is predictable, it allows your player to feel smart by saying like, oh, I know what this AI is going to do, so I'm going to plan against that. But decision trees are good for games with player choices with unique pre-designed experiences. Visual novels, dialogue trees are a good example. Simple agents, if they have a small set of actions that they can do and it's easy to decide which one. And resource management games. All of these games are based on just making simple decisions. So it may be simple, but if this is all you need, just use this. You don't need to get super fancy with your AI. Some resources, if you want to learn more about decision trees, are there's an explainer here from UMD. There are several packages for Unity, Unreal. You can do it in blueprints. And in Unreal and Godot, there are no packages, but you can write code also. So the next type of AI is called a rule-based system. Here's another example of a might use rule-based system. And a rule-based system just has a list of rules to follow that tell it which action to take. It typically goes through these in some kind of priority order. For example, the first rule here is if your hit points is below 25%, you just run away. And you can see the rest of the rest of the rules here. It'll just follow these, and it'll give them lots of variety of actions depending on the number of rules that you have. And you can order these just in a linear order like this, or you can priority rule. So the pros of this is that it typically runs very fast. And as you can see, it's just a list of rules, so it's fairly easy to implement. It's simple to understand. This is probably one of the simplest to understand and debug because it's just a list of rules. But again, it can be repetitive. It doesn't handle uncertainty very well. And if you have a lot of complex rules, you can use something called an inference engine that is used by expert systems to really churn through those rules to find the best action to take. But that's a little more complex. I will point out some resources at the end of this talk that that have some good explanations of, or really good example code on how to implement a simple inference engine for game. So these are good for turn-based combat, like that JRPG that I showed previously. D&D, Dungeons and Dragons, is rule-based. It's good for simple arcade games. It's good for schedules. If your town NPCs do things at different times, you can make those rules based on times, other factors such as is the town peaceful or is it under attack? And it's good for expert system type games. These are games that question and answer type games. So some resources for that. There is an expert system inference engine for Unity that I've linked here, and in Unreal, you just write in C# if you need to. And there is a rule-based system for Godot also. So the next type of AI, and probably most people have at least heard of this, if not implemented it all over the place, is the state machine or finite state machine. Here's an example of a state machine on the left for a game called Gestalt, Steam, and Cinder. And the idea between a state machine is that the agent is in one state, a finite state, and it can switch between these different states, which define different behavior that the AI is doing. You might start at the wander behavior, and then it transitions based on conditions. So it's sort of similar to the decision tree, but a little more complex, with the advantage of that complexity giving it the ability to scale a little bit better. So if you're wandering and you see the player, you chase. And if you chase and you're near the player, you attack. If you lose sight of the player, you wander again. You can see how this works. And again, this is relatively simple to implement in code. Here's some pseudocode for this finite state machine. Pretty simple. The pros, easy to implement, simple to understand. You can see with these states, each of these states can be relatively simple. So it's easier to divide and conquer rather than having to look at an entire decision tree and figure out how you're going to add new decisions into that. And there are a lot of visual editors, so designers can implement the AI. I'll go back to this example here. These finite state machines are done visually in this tool here called Canvas. But the cons are that when you have a lot of states that have a lot of transitions, you can get what's called transition spaghetti. I'll go back to that one. You can see here that there are a lot of arrows pointing from state, and this is for a relatively simple but smart agent. So if you had twice as many states and they were all transitioning to each other, it gets a little bit messy. And it's not particularly flexible because it just has these rules to always go from state to state. But even with all those cons, finite state machines are good for everything, like input handling, menus, light switches, doors, just about everything. And it is one of the fundamental forms of AI used in games, often in conjunction with other types of AI. So it's good to be aware of how these work. Some resources are here for Unity, Unreal, and Godot, and I will drop the slides in chat after this so that you can just click on these if you're interested. And here's an example of transition spaghetti if we just added one extra state called flee. So we have this state where if the player is in, or if the agent is in the chase state and they get hurt, they switch to the flee state. But if they're attacking and they get hurt, they switch to the flee state. So we just doubled the amount of arrows. There are a few ways to address transition spaghetti while still being able to take advantage of the relative simplicity of state machines. One is called the hierarchical finite state machine, where you have two state machines here and a transition from one to the other. So regardless of where you are in the normal behavior FSM, if you get hurt, it always just switches to this flee state machine. And when the agent is healthy and doesn't see the player, it just switches back to this same normal state machine. In this case, for hierarchical FSMs, it typically, whenever you transition to one of these sub-state machines, it just starts with whatever is designated as start state. However, there is a variation called a push-down automaton, which before you transition, it records which state you were in. And then when you return, it returns to that recorded state. So that's the essence of the difference between a hierarchical FSM and a push-down automata. There's another way to handle the complexity, and that is layered finite state machines. I've done a talk before, but this involves creating very simple state machines at different levels of granularity, where the higher level subsumes responsibility for the lower levels. That is, if something at the squad level says take some action, then the FSMs below will follow what that higher ranking FSM tells it to do. And likewise, these lower level FSMs, when they do something that needs to be reported back up to a superior, they report those back up. So again, another way, and you can look up any of these techniques if you think they would be useful in your games. If you want to avoid all these state machine variations, there's always the behavior tree. So here's an example of a behavior tree from Halo 2. And the way this looks, it looks kind of similar to either a decision tree or there are special types of nodes in this. And notice this is a node. I mean, a node graph, graphs are so fundamental to AI. The question mark node here denotes a selector. That is, it looks at each of these in turn and tries to find one that is like valid at the current time. And then these arrows here are called a sequence. It tries to run children in order. So let's say our situation for this agent is that the agent is healthy and sees the player in the distance. So when it evaluates this behavior tree, the selector is going to look at this sequence and it's going to check, am I hurt? And since he's not hurt, this sequence is going to fail. So the selector will go here to this sequence and say, can I see the player? And if so, chase. The chase might have a condition where if it's close enough, it's done. And then in that case, it would move to attack. So behavior trees, they're flexible. They can give you more reactive seeming behavior. And you can see that they can be more succinct here than complex finite state machines. Again, there are editors available for this. So non-coders, designers can create and tweak the AI, but it is more work to implement. And typically it's designers or level designers, programmers who are designing these behavior trees. And it does require planning just to make sure that you have all of the bases covered. And just like with finite state machines, they're not adaptive. They do only what they've been pre-programmed to do. They are good for reactive AI, especially when the AI has many more actions than would be practical in a finite state machine. Great, obviously, for combat games. And if you want to learn more, there's another great explainer and various tools in all of these three game engines as well as other game engines. So the next one, and we're getting through these, so we'll be done with these pretty soon, is a game tree. This might be familiar if you've heard anything about how computers play chess or checkers, or in this case, tic-tac-toe. So the idea here is that it follows through possible plays of the game to identify a path that produces a good desired end state. For instance, this is one where X wins. So we give this a rating of +10. Here's another one here where X has +10. But given this state, we would probably choose this one because it's nice and quick and the player wins. So the idea behind the game tree is that you build out this graph again, and you follow the path till you find an ideal state or as close as you can to it. Often done in chess. So the pros, it's fairly easy to implement a basic tree and to trace through. You can see here visually, you can just trace through and figure out which are the best options to take. And it can give an optimal solution, which is something that other AI will you are programming the decisions. You might not have thought ahead of time of what an optimal solution is. But in games like chess, there is combinatorial explosion. That is, the tree gets just way too big to really analyze the whole thing in one shot. Now, there is a lot of optimization research, and I will talk about that here in a second. It's good for resource optimization games and perfect chess. And here's some great explainers. In fact, this first YouTube video here, she does a fantastic job of explaining game tree. So if you are doing any kind of a board game, that is definitely the video to watch. Nice and simple, easy to understand. And I'm putting just some terms here so that you'd be familiar with different ways of analyzing and optimizing your game trees. So for AI that is not just reactive, but seems a little more proactive, we have hierarchical task network planners. So these are famously used in guerrilla games such as Transformers and Horizon Zero Dawn. Here's an example of a visual editing in Unreal. And so what this does is it generates a multi-step plan in real time, and it breaks this down into small steps, like locate a firearm, move to it, pick it up, and attack. And then once it has that plan, it follows those until either it's done or something has invalidated that plan. For instance, if someone else grabs the firearm, when it gets to the grab firearm action, it can't do it. So then it replans. So this, unlike the previously mentioned techniques, can provide proactive behavior because it really seems to plan ahead and think about more than just the immediate situation. There are editors for this, so designers can implement these. And sometimes, as far as I'll just jump down to the last one in the cons, is sometimes this emergent behavior can be a little bit unexpected because they could come up with a plan that you had not imagined when you originally made this tree of different possibilities. This technique is good for seeming like the agent is creative and being able to come up, and great for more sophisticated NPC. Some resources for this. The University of Maryland is known for an HTN planner called SHOP. So our local researchers here are on the forefront of HTN planning. In Unity, there are some open source approaches. There is a plugin on Unreal Marketplace or FAB for Unreal. And in Godot, there is no HTML, but you can write it in code. The reason why I'm mentioning these is that all of these AI techniques really are, even if they're not familiar now, within reach of indie developers. There's no need to be intimidated by any of these techniques. And that includes goal-oriented action planning. So this was made famous by the game Fear and similar games designed by Jeff Orkin, who's an AI researcher and designer. And the idea of goal-oriented action planners is that you start with a world state, like the agent is on one side of a messy, and a goal world state. That goal world state might be kill the player. And the agent generates a sequence of actions, a plan, that will transform the current world state to the goal world state. So, for example, a plan that will kill the player. So it essentially builds a search tree on the fly. And again, this is why pathfinding and searching is so important to AI. I'll show an example from one of my tools called Quest Machine. In this example, we have a quest-giving NPC in the upper left, whose goal is to ask the player to handle these pesky orcs down at the bottom of the map. The way she will accomplish this goal is through a library of actions that could be done. That includes getting an item or picking up an item, killing an enemy, or polymorphing an enemy. Now, this pirate is, despite looking like a pirate, is a nice pirate, so she doesn't like killing things. Let's take a look at the first action here. The get action has a prerequisite that the item exists in the scene, and the effect is that the quester, the player, once this action is complete, has the item in hand. Now, if we look at the polymorph action, the prerequisite is that the enemy exists, the orc, for instance, or these wolves, and that the player has the wand. And the effect of doing this action is that the enemy is gone, and then a rabbit exists because the wand has polymorphed the orc into a rabbit. The way Gope would go about generating the plan to do this is it starts and looks at all of the possible actions that could be done. One of them is getting the wand. One of them is killing an orc or killing a wolf. Now, we could stop here at killing the orc, but she would rather not be violent. So we can expand these actions. If we expand the wand, the possible actions available from that state are killing the orc, killing the wolf, or polymorphing the orc. So here we find a plan that that the AI agent would like to see accomplished in a way that she'd like to be accomplished. So the plan is get the wand, polymorph the orc. And that's simply how goal-oriented action plan works. It just navigates this tree of world states. So the pros of this is that you can really create the most complex proactive plans of all of these techniques that I've described so far. You can get really interesting emergent behavior. Fear was famous for that, with AI doing all kinds of creative things. And it adapts well when the world state changes because it is generating these plans based on the world state. It is moderately complex to implement because these trees can get very big. It can be a memory and performance. It is possible to, and it does take time to design this library of actions. But the more actions you have, the more interesting the AI can be. So this is good for games where agents have lots of ways to achieve their goals and the world is unpredictable. Some examples are Fear, Shadow of Mordor is another game, Quest Machine also. Some resources for this are Jeff Orkin's famous paper, Three States and a Plan, AI of Fear, and a good GDC talk on that, kind of like a retrospective of that and other uses of Gope. Unity has a good tutorial on it, and there is a Unity programming streamer who goes by the name Get Amend. He does, his videos are fantastic. I can recommend them for any topic that he does, but he does a good goal-oriented action. There are several tools that you can use to implement Gope in Unity and in Unreal and in Godot. I'm sorry, I'm only mentioning these three, but there's only so much. So the last of these traditional types of behavioral AI to go over is utility AI or needs-based AI. In The Sims really made this type of AI famous. And the way it works in The Sims is that an agent in this blue area in the upper right has a number of needs. Hunger, comfort, hygiene, etc. And as these needs get more important and need to be satisfied, the sim or the agent looks in the scene for what are called smart objects or objects that advertise that they will address these needs. In this example, hygiene is getting pretty bad. So the sim is going to look around and see what in this scene can address the hygiene need. And it'll choose this shower here. So once it's chosen a smart object, it simply follows a finite state machine that is defined on the object, which includes walk to that object, play an animation, play a sound, and increase the hygiene. Um, it is This FSM is super simple, and um, it's this combination of FSM and needs based makes this seem so interesting. So the pros of utility AI, it's easy to implement and visualize. If you look back here, you can look at all of these needs and right, and you can see, oh, what is the AI needing to do next, and it efficiently models these changing needs in real time. As these needs go up and down, it's able to adapt to that. Uh, I'll get to this bottom pro in just a second, but the cons are it does require a careful balance, and your game area needs sufficient ways to satisfy. If there was nothing to satisfy hygiene, the sim would be very sad because they'd have no way to address that need. And this is a decision a decision technique for AI. It does need a separate behavior handler to act on that decision. Back in the pros section, this technique works well with what's called fuzzy logic. Instead of a yes, no on should I eat, there can be kind of a gray area, and then all these different areas needs. It helps you more fluidly decide which need to satisfy first. And it works great with smart objects, which I mentioned before, are objects that are tagged with what's called affordances or benefits in the scene. Quest Machine also uses smart objects. The wand, the orcs, those are smart objects that say these actions can be done. So utility AI is good for games where are driven by competing desires, like The Sims. Age of Conan uses, because it's a survival game. So all of your thirst, tiredness, hunger, health are driven by utility needs. Far Cry, I mentioned before, has the Cry engine has something called an AI anchor. And as an agent's need, for instance, a need to tinker gets high, then it chooses a smart object like the pickup truck and goes to it and does whatever animation is. And Quest Machine is another one where it uses utility AI and smart objects. So resources for this include Mark Brown's talk about The Sims. That's a good intro to it. Kevin Dill goes over how they implemented AI in games like The Sims. And then there are several plugins and open source tools and videos for Unity and Unreal and Godel. So the next form of AI, probably not quite so easily in reach of indie devs, but it's good to be aware. And this is probably something that's more to Julian's interest here, and that is reinforcement learning, or racing games in particular use this a lot. So the idea is that you have an agent that just tries an action, and that affects the environment. And then based on a reward function or an outcome function, it is told what the new state of the environment is and is either given a reward or a punishment. And it just keeps doing this until it learns what is good, that's the gist of reinforcement learning. It's actually significantly more complex than there are a lot of tools for it. It's good for generating novel solutions to complex problems, and it's very adaptive. But I will skip over the cons. Let me just say that it takes time to train these agents up. and it can be complex to implement. However, I'll mention something about that in a second. So that's good for non-deterministic, frequently changing environments like racing games. It's also good for strategy games. There are a lot of machine learning examples for games like StarCraft. I mentioned racing games. And there are a lot of resources if you're. So David Silver did a great DeepMind AI course on this. Unity has their own ML agents package, and they have lots of tutorials for that. So if you're using Unity, you can jump in and experiment with this right away. Unreal also has a bunch. And Godot partnered with Hugging Face for a reinforcement learning course. So plenty of resources if you're interested. Do keep in mind though that this is like a completely different approach to behavioral AI as all the previous. Now, the last thing I want to talk about is AI directors, because I get questions about this. An AI director isn't for a single agent, but rather the behavior of the game as a whole. Left 4 Dead is a famous example of using it. The idea here is that it dynamically manages the pacing, for instance, the number of zombie spawns based on the current game state. So the AI director uses a where it might be in one of these states, like a build-up state where it's spawning a lot of enemies, and then a sustained state where it just keeps the pressure on the player. And either when they've, to avoid the player getting bored with just the same amount of enemies, or if the player is getting overwhelmed, it will fade off from that peak. But it's doing this based on the current game state. It's looking, hey, is the player getting overwhelmed? Taper off, and then it kind of relaxes to give the player a breather to simulate that sort of ebb and flow of combat, and then it goes back to building up. Um, this is an example of how the number of spawns might happen during the course of a game, where it's building up, it's peaking, then it fades off, then they get a breather, and then same thing, and it just repeats like that. This is a screenshot from a talk done by the director of Warframe, another game that uses an AI director. And this is good for, I mean, you can use this in shoot 'em ups, bullet hells, any kind of game where you need to like have an ebb and flow in an amount of. Here are some resources for that if you are interested in AI directors. So that is what I have for behavioral AI. Some great resources for learning about these books on the left, AI for Games and Game, and videos from the Game GDC or Open Access, which is a resource for accessing academic papers. Some of those academic papers can be dry, but some of them are gold, and it really depends on the quality of the writer. If you're really lucky, you'll be able to get your hands on this fantastic series of books. They are a little older now, but I was just looking through these recently, and man, these books have so much great knowledge in them. So if you ever find them at a used bookstore or you ever have access to them, just look through them. You'll be amazed at all the interesting techniques that AAA pros, indies have shared in this series of books. And that's all I have. So thank you. Are there any questions that anyone has about this or any thoughts?
No, no questions. I was just, I thought I was familiar with AI. I didn't realize there were all these different types of systems. So this has been actually very informative for me.
Oh, yeah, thanks. Yeah, I'm glad. Let me see if I can get back to Discord here in case anyone has put anything in chat. Um, let's see. Yeah, Rick writes Dragon Age Origins I will drop these slides in the Discord server. And Rick mentions FSMs are great. Yeah, they are. They're like the basis for a lot of interesting. So
Is there
go ahead.
I mean, I guess the question I would have is, and I would assume the answer to this is probably no, but is I guess I'm trying to I want to say is scale like the 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 factor that kind of determines which one of these systems you choose? I know that's kind of scale is not a very exact term, but I guess complexity is maybe a better one, like AI or enemy complexity. Is that kind of what dictates which one of these systems you choose, or is that not?
Yes
Is
and
that
no.
Mhm.
And that's part of the reason why I tried to give this toward designers also, because yes, definitely, since most of these are graph search problems, scale and complexity are are a big consideration. But in addition to that, some of these techniques like GOP and HTN planners just behave differently because they provide more emergent behavior. So if you have a lot of, if the world changes unexpectedly, or if you want your AI to do interesting things that you have not necessarily pre-programmed, then you might be interested in GOP or HTN. But if your AI has simpler needs, a behavior tree or a finite state machine will work great. Another, utility AI is because then you can base it not so much on the individual actions and the network of actions, but looking at it from a completely different vantage of what does this AI need? And then from there, you determine your actions.
Yeah, that makes sense. That makes a lot of sense. Okay. Is it if you say you pick one, because I mean, throwing together a behavioral tree seems, I mean, relative to the other ones, somewhat easy or at least straightforward. If you decide that maybe that isn't the best choice to go with, how difficult is it usually to switch up to, like, say, like a behavioral tree? Okay, I need something that's a little bit more emergent and go to something like Gove.
Uh, you know, it is possible to merge some of these. Like there are goal deciding tasks available for you can define a task in your behavior tree that says like or what is my current need, and then it follows that branch down the tree. But as far as the actual algorithm of behavior trees versus go, they're so different that I think what you would want is modularize it so that you can pull out the entire behavior tree thing and swap in GOP without having to modify the other parts of your agent, such as their animations or their health.
Yeah, yeah. So you'd almost have to know that you were switching it out before you started your design, which is, yeah, okay.
Yeah, well, that's why I
Yep.
wanted to do this high level overview so that you're aware of all these things ahead of time.
Yeah, yeah. Okay. All right. Thank you.
Yeah. Okay, Rick says, do you know of any good resources for strategies to templatize a core AI that's designed for derivative variants? That's a good question. Um, a lot of these can be templatized in various ways. GOP, for instance, you can say maybe your dumb enemies only have access to a limited subset of your library of actions. So then that will limit what they are able to do versus your brainiac agent or your agent that's very versatile. Um, Same thing with behavior trees. It is possible to create kind of like nested behavior trees or um, finite state machines or layers of finite state machines where Some of them have access to a lot more states, but it can generally be a little bit difficult to templatize a lot of these things if you're taking advantage of visual editors for them. But then again, visual editors make it possible for your designers, to go ahead and create and experiment with these things without programmer intervention. So that's a good question. Unfortunately, I don't think there's a good answer. All right, well, I will call it there, but if anyone else has any questions, feel free to drop them in chat.